welcome Messoud Efendiev, who I met through Herman, right, when you had your thematic program.
Yes.
Messoud, I think even at the 65th, where you wrote the foreword to the special edition, you mentioned that in every talk there's a figure, sits on the side and always has questions to ask. And he's so we started talking, and of course, Messoud, I realized that at some point, I had been using the Ray-Schauder degree to prove something in buoyancy-driven flows, and of course, Messoud comes from the Kolmogorov school, where they really understand what the Ray-Schauder degree is about and how you can apply it in every situation. So it's been a pleasure working with him, and of course, he's a very distinguished record. He was Humboldt fellow. Also, he came as Dean's Distinguished Visiting Professor during that thematic program. And he visited Waterloo as the first James D. Murray Distinguished Visiting Professor. The interaction is with everything we always find is as much social as mathematical. And it's been a great pleasure interacting. In fact, both Herman and I don't know if there's anybody else, went for his birthday celebrations in Baku. Very memorable meeting, and good mathematics, but much more interesting other activities.
Yeah.
Anyway, so welcome, Messoud.
Okay, thank you very much, Steve. It's a really great pleasure to be here. And, this is a Fields Institute, or for me, this is as the second or third term. And then you mentioned this. I would like to just come to nice pictures, which I hope I have it. Yeah. So that you see that I choose the picture where you can see Herman as well. And that this is the Herman. You see that, and this is Sid. So that it was, as you said, it was in Baku, in Azerbaijan, in my 70th birthday. So now let me explain, in contrast to the previous talks, the following. I will speak on the combination of how the biology has an impact to mathematics. Not the mathematics has the impact to biology. And one of the crucial aspects which I am trying to do, that I would like to say that as Steve mentioned, I met him around 2018. And since that time, we have collaboration. Even we wrote 2 papers. And now the third is submitted. So this is the related what we did. And we started with him in completely other aspects of mathematical oncology. So then ultrasound, tissue. And then, but today I will touch the other issue. I will deal with the mitochondria. And this is also very important. This is directly related to the topics of the conference. And but before to do this, I would like to thank the organizers, because they organized this conference in such a way that since yesterday, I changed inside, but not changing the whole topics. So yesterday arose a couple of the questions. I would like to immediately reply to that question as well. So this is really related to what I am going to do. And then since yesterday you heard, so that I will so that these 2 topics which I'm trying to do, the one will be I didn't want to touch this question, but this was the related yesterday questions. Therefore, I will catch a couple of things here, because the behind of this is the predator-prey model. On the one hand, on the other hand, this is the equation which we derived, or the Herman's and his co-author as well. So that this is exactly the same question which arose yesterday. So then when you are looking the macroscopic limit, you have to have in the limit divergence and gradient like this. not that from the beginning. So that this I will touch these questions very quickly, and then later, of course, switch to the main topics of the mitochondria. So are you hearing my voice? It's okay. Very good. And then, so then, first of all, let me just look the biofilm. So that just a quick, because the biofilm is accumulation of microorganisms, and then belong to one of the successful life form on Earth. So this is the such a kind of the accumulation or the collection of the cells in the, if you want, in the population scale. And then the other issues will be the mitochondria. This will be exactly the topics. And what these two models has a lot in common. So then this is I would like to just give a message. So that both of them, in contrast to all talks, which was the yesterday, and also before the Thomas did. So this will make a crucial difference. So both of these model based on the experimental setting will give a new class of in mathematics. So this is the effect on biology to the mathematics. I will show you. So the new class means that this will be degenerate parabolic type equation. So the old equation which you have seen yesterday was the non-degenerate. So the either Laplacian or somehow it's kind. But and you will see that how the degenerate coming from biology will impact dynamics of the equations and long-time dynamics, which in the end the Thomas tried to persuade us, and afterwards how we can select the patterns depending on this issue. So again, so this is if you want, maybe it's not so modest to say, so this will be the conceptual, the asking or bringing or the giving the idea. So this is, it's time, if you are really trying to understand the effect of biology or oncology, so then there are time to switch from the diffusion, the classical diffusion, to the density-dependent diffusion. But it's not necessarily for all, but sometimes if you would like to catch deeper. And then this is the equation which I am trying to understand. So this is the, let me just start the equation which I am speaking. So then this is the single species, single substrate. And you will immediately see that how we can extend to the yesterday's talks with the antibiotic effect on antibiotic disinfections of biofilms, as well as antibiotic effect of the cancer cell. So that this is the equation. This equation can be derived very strong way. So they're using the macroscopic limit. And then the crucial, the novelty here, this is the density-dependent diffusion. So this is, for all of us, it will be ideal if it will be here as in the talk of the Thomas. So it will be here the 1. So the density dependence, it's 1, and then it will be the Laplacian, and then we will have the similar type equation which the Thomas considered. But here is not the case. Here then the biology required to consider this, and then you see, and this is the crucial difference when you have when you have here the density dependent diffusion, the 1, then you obtain here the Laplacian, and then for the first equation you have the Laplacian. The second equation, if the density dependent will be identical to 1, then this this you remain in the sense of the mathematical tools. So you remain, and then please, if you have questions, please immediately interrupt me, please. And then if you have here the identically one, this is, we are in mathematics, we are calling this a density this is non-degenerate equation. And this kind of equation has a very interesting property. So then if, so which is the physicists say the infinite speed of propagation. So that means that if the initial data will have the complex support, so you see that then in the next time, then you will lose this effect. So then this is a very important property, which this is a mathematics. So this is you can use a lot of mathematical tools. But as soon as I said, the experimental information coming from the biological experiments. So that means that this is not identical one, or this is not so-called or similar one. This has the two kind of degeneracy. This I am calling the new class of equation. So that you see, so the one hand is density dependent. On the other hand, they has a two kind of degeneracy, which is called the porous medium and singular diffusion. And this has the very big impact to dynamics. And this is I would say that this will be, if I will have time, I will speak on it. But this is the new chapter on dynamical system. And the second one is that I would like to connect this, my talk with what was yesterday, and with the main topics is that this is the effect of the antibiotics. So that this is please, thank you very much. So this is the following. If you are dealing, if you have here the one, so the Laplacian, if you are solving even the heat equation, if you want, then you see that if you have the initial bump, as a compactly support, the diffusion is so strong that they are pushing this away, and then this therefore you are lucky. You have that means you have the enough regularity to handle with your mathematics. Here, then in our case, which is coming from the biology, in our case we cannot do that because here we have, you see, we have the porous medium type. So this, as soon as you are hearing the porous medium, this is physics. And the porous medium, then so first of all, we lost regularity, if you want, as a mathematician. So then we cannot use the standard apparatus which we have in mathematics. We have to think like physicists, construct some solution by hand, if you want. And then here, this is which is called the finite speed of propagation. That means if your initial data has a compact support, and this profile remains all time. So, and this is and then you lose a lot of things. It makes mathematics difficult, and it's really you should not think now that at this moment like the mathematician, because apparatus doesn't help. Good, and then so then this is we understood. Then because you can say that you see in biology we don't have single species, single substrate. We have the multi-component models. I will not go into detail because this is related to yesterday discussion. Therefore, I would like to just remind you that if this is the similar things which we have. So that this is we have the X is the biomass, the density, and then this is the killed cells, and this is the oxygen, this is nutrients. So that this is this kind of the equations give us the information, as I asked before Thomas. So that having the different time of different. This is a multi-scale modeling, and having a different time of the scale, we can find so we can find the number when this is antibiotics, where this the other part of win, and then this is the what I would like to connect this with the yesterday discussion. Therefore, again, thanks for choosing the participants in a way that then you can follow and then discuss the question which was that. But the other things, so as I said, here we will have a lot of interesting questions. So yesterday I asked the Helen concerning to Darcy law. So I will not touch this. This is what we are now trying to deal with, so-called the ODE-PD coupling. You see that appears such a kind of the traveling wave solution. So then, therefore, I will not touch. So, and now let's come to the case which I would like to discuss with you. So this is mitochondria. So how many times I have? 12 minutes, 12 minutes, good. So now the idea is the following. So this is directly related to these the topics of the conference. This is I am interested in mitochondria swelling scenarios. Mitochondria, as usual, in many years considered as the power house of the cell, due to the main its property bringing the energy to all eukaryotic cells which we have inside of our body. And it was astonishing, it was really very unexpected that the mitochondria could have impact also in apoptosis scenario, so the program cell death. And similar to Thomas, in the Helmholtz Center, just in the building where I am working, so this was a couple of buildings on the north from our building. It was the Institute of Pharmacology and Toxicology. And then one of the experts came to us and asking me, could you explain mathematically? So they observed in experiments. So this is the, sorry. So this is the mitochondria, which is not swelling. So they did the in vitro. And then this is the non-swelling mitochondria, and this is the swelling mitochondria. And then this is a very crucial, because if you have the swelling, so then I will touch these questions. Mathematically, we are coming to equation later, but they understood that if you have if you are initiated, so the mitochondria swelling, this is the one is very important, and this is a reversible process. And then under certain circumstances, in mitochondria, so then we have here, you see, we have the outer membrane, and then we have the inside the inner membrane. So the cancer cell be killed, must be killed, or should be killed, or we expect to be killed if in somehow, then I will touch in which sense somehow. So the inner membrane expanding or swelling, touching the outer membrane. And since the area of the inner membrane is the high magnitude, then the outer membrane is rupture, and then swelling and apoptosis started. So this is a very natural, this is organella in our body. So then you have to understand that if you would like to kill the cancer cell, you have to initiate some kind of the swelling scenario. And then the swelling scenario started when the inner membrane somehow started swelling. How it can be? So then there are several ways that the people doing, and they also our co-author from Institute of Pharmacology and Toxicology. So they did in vitro, and you have to have something which is the capacity of our body give us the possibility to handle with this. And that's why one of the mechanism which is initiate swelling scenario is the calcium, which is the one of the transporter. And due to if you have the calcium load, and this is a load calcium, the crucial things that as I said, we have the two compartments, the outer membrane and the inner membrane, and so they are different as far as concerned the permeability. So inner membrane is absolutely impermeable. So in comparison to the outer membrane. And then as soon as you are in the position to make somehow the pore inside of the inner membrane, then through the difference of the gradient, some molecules, they can move from the inner membrane. So you have the pores, so that they have some, the molecule can initiate swelling, and in this way, there are the process is started. That means the calcium is one of the key ingredients to handle with these questions. And so then, as I said, this is the irreversible process. We understood that if you are dealing with in experiments, then now I will come to the equation. So then, so this is what we received from our colleagues. And then we started to understand how we can explain that how we initiate this process. So that therefore we take the following the variables following the component. So we take, as I said, here the calcium concentration play a very important role in order to initiate swelling process. So this is and then experimentally, it's well known that the mitochondria, so which is, I say, this is such a kind of organella, they are have the three portions, if you want. So the one of them is called the unswollen mitochondria. The other, the swelling, during the swelling, so that you have the intact mitochondria, and then you are initiating. But this, if you have some swelling mitochondria, it's not enough to initiate. This is the apoptosis scenario. So that then you have some transition from the intact, from the unswollen, swollen, and completely swollen. As soon as you have the completely swollen, then the apoptosis will initiate, and then the equation which we understood during this our conversation, you see there is some parallel what the Thomas said. The other guy from other building came to ask questions. So there are some similarity. So they, of course, they don't know what is the behind of this equation. And as you see, so then this we have the three component, and one, this is the unswollen, and two, the swollen, and then three, the completely swollen. And depending of the calcium load, how many times I have? 3 minutes, okay. And then we understood completely in a mathematical way. So then when we have the apoptosis scenario, we can start when this we don't have these. And as you see, this very nice mathematics here. And then, as I said, as before, here, this is the, you see, for first equation, we have non-degenerate parabolic equation, all right? So that this is we have the Laplacian. It could be here the fractional Laplacian. So that this is the mathematical apparatus for this is enough to handle with these questions. And then the other part is it was the in vitro. We are considering omega, where we pose. This is the test tube, and in vivo this is the whole cell, and then this is the standard the equation. But this is the important. This is the ODE-PD coupling. And please. So actually this is the inside. So this is the in a membrane. So this is we are calling the calcium buffer. So this is the interesting point. I will come to this because this term what you are saying. So you see that this is coming what the very well located this calcium. Initiate. So this is one of the scenario. You are right. So exactly. So there are two waves initiate. One, as you said, so we have the external stimuli. Other the inside. Inside. Please go ahead. Yes. Yes. So exactly. So that. But in order to have this filling, as she is asked, so that you have to have enough capacity of the calcium slot. So either you are doing either you are doing from external, or you are using the capacity of the cell inside of our body, which is say the inner membrane has the you see when the swelling started, the very this is observed in experiment. So there are something inside of our body. This is hidden mitochondria. As soon as the process started, they are woke up, and they are doing. So our body is very interesting. Yes, exactly. And then so that this is the you see. Then we completely understood here, and the biologists tell us that look. So you see. This OD part means that the mitochondria doesn't have the special movement because this is OD. So that, but some biologists, this is not completely clarified yet, but it's some biologists saying that this is the mitochondria can move also spatially. So then we have to put here. So also the Laplacian N1, Laplacian N2, Laplacian N3. So this make even our analysis easier because we have the regularity enough. And now for me, so there are, this is together with Hermann Abel and the other our colleagues, we completely understood the mathematics, what kind of the mathematics can be initiated here. But my message to that, so in experiments, the people observed that because mitochondria inside of our cells located near the nuclei, that could be near nuclei, near membrane, and also the main source is the endoplasmic reticulum, where we have the calcium. And depending how we are mitochondria or the calcium is close to them, we have the different scenarios. And in order to capture these different scenarios, I would like to, this is completely understood. I would like to just say that, so maybe, so I'm not sure, therefore I like fields, that's why sometimes you have to jump to here and then suggesting something which will be maybe useful or may not be. So that consider this is non-local effect, which could capture what I said, depending how the calcium load or the higher degree is close to endoplasmic reticulum or the nuclei or the boundary of membrane, we have numerically different scenarios. I guess this can be captured by such kind of the non-local effect. Thank you very much for your attention and the questions.